now we'll talk about the continuous time martingale. So it is, you will see that basically similar to the discrete type of martingale, but here now I have time continuity. Time continuity in the sense that it is not time continuity, means there you have sequence of random variable. Now I have basically that process t, which lies with t, basically the index set is now that 0 to infinity. Okay, open 0 or maybe close 0 to infinity. Okay, so previously index set was the natural number, set of natural number, say 0, 1, 2, means it includes 0, maybe 0, 1, 2, and so on. But in this case, index set, the t, whenever I define a stochastic process, no, it is basically set of or the family of random variables indexed by this capital T. T is from T, means for each T, X T is a random variable. So now continuous time Markov chain means again the state space, it may be finite or may be countable. Okay, so it may be finite or may be countable. But the domain, in particular the time domain, it is 0 to infinity. Okay, and also, so continuous time Markov chain means basically it is again a Markov chain, but it will be a discrete time Markov chain if you discretize the times, suppose t1, t2, tn up to t of n. So in particular, what I'm saying is the following. I have a stochastic process xt. T is positive with say countable state. So it may be finite. No, in general, it is countable state space. With countable state space, say S. Okay. So now we say that it is a CTMC. So xt is a CTMC, means continuous time Markov chain. If the following holds, so consider that probability of x of say t of n, which is my state j, given say x of t1 is equal to maybe I1, x of t2 is equal to I2, and so on. X of maybe t of n minus 1, I of n minus 1. If these things is basically given by probability of x of t of n is equal to j, given x of t of n minus 1 is equal to I of n minus 1. Okay, this should hold for all j, I1, I2 up to I of n minus 1. They are in my state space. And how I am choosing this discrete times, they are nothing but that 0 less than equal to t1 less than t2 and so on. And this should hold for any arbitrary n. Okay. See, this is exactly whatever I have done. If you just think of my y of n is equal to x of tn, then in this discrete time points, yn is a DTMC. Okay, so this is the same definitions. So if you want to predict or the probability of xn is equal to j, given all the history, this is same as probability of xn is equal to j given the present time, means x of t n minus 1 is equal to I of n minus 1. Okay. So for any any time interval, any time discrete point, 0 less equal to t1 less than t2 less than tn, if this holds, then we say that a stochastic process xt, it is a continuous time Markov chain. Okay. So another is, so like in we also define there that homogeneous the DTMC and so on. That means depending on the probability. So here also I can say something similar things, but little different way. Because here you have time things. So I'm saying we consider probability of say x of t plus s is equal to j, given x of s is equal to I. So you start with at time s. Okay, at time s, process start at position I. So now in at time t plus s, so there is no step, no, because in Markov chain we are saying that okay, in each step say at n step actually I am having in this position j, that means it is actually now it is at time t plus s, it is in position j, and I'm looking for that probability. So if this is independent of my s, okay, and it holds for all any t, then CTMC is homogeneous. That means I can think of, no, so if I denote something like that, say Pij of t, I'm denoting this is basically probability of x of t is equal to j given at time 0, you start with state I, at time t you are in a position j. What is the probability that this is my Pij? So I can write down, if it is a homogeneous CTMC, this I can write down probability of x of say t plus capital T is equal to j given my x of capital T is equal to I, is it not? So basically what it says that it does not matter at what position I started, only basically the time differences. If time differences is basically t, then okay, in case of my homogeneous CTMC, as I said, like in DTMC case, we are also considering here the homogeneous time Markov, continuous time Markov chain. Okay, so this Pij, I am finding a matrix P, which is my Pij, small Pij over Ij, which is in my state space. So this matrix P, this is called again the transition probability matrix. Of the given CTMC. Okay. So this P is a transition probability matrix of the given CTMC. Okay. So as I said that throughout our discussion, we will consider a homogeneous CTMC. Under this homogeneous CTMC, you can check the following. This is simple. Okay, so now Pij T, this is nothing but probability of, I can think of xt is equal to j given x0 is equal to I. The process start at time 0 at position I, and it reaches at time t in position j. And what is the probability? That is, I call it Pij. Then you check, it is simple that 0 less than equal to Pij of t less equal to 1. And this holds for all t positive any ij in my state space. Okay. And I can think of Pij of 0. So by definition, this is probability of x of 0 is equal to j given x of 0 is equal to I. So it is, I can think of it something like the delta ij. So if ij is equal to I, so because what is the at time 0 you start with I, and then at time 0 you will be in position j. What is the probability? That should be delta ij. So either it is 1 if I is equal to j is equal to 0 for I not equal to j. And not only that, you check yourself that if you sum it over j of Pij of t. So for discrete time Markov chain, whatever I have, the similar thing, no, summation over j Pij. If Pij or Pij of n for the n step probabilities, transition probabilities, that gives you 1. So this is also same holds for all t is positive. Okay. Okay. So now simple example of a continuous time Markov chain, that suppose at time 0, suppose you have say n computer is operating, okay, and then they have some lifetime. So suppose their lifetimes are independent and identically distributed, maybe with exponentially random variable with parameter say lambda. Then if I denote that xt at time t, which is the number of computers which operating at time t. So then xt, you see that it will be a CTMC, okay, and what is the state space in this case? It should be 0 to up to n. So that means we have capital N plus 1, okay. Okay, so like in discrete time Markov chain, what we have proved that Pij of n, what I write down that summation over j Pik r and then Pkj of m, something like that. No, we have wrote down, or something called the Chapman-Kolmogorov equation. So then question is whether we can deduce the similar thing here or not, because you have already seen that this Kolmogorov-Chapman equation is really important there. No, if you try to find out the n-step probability, probability matrix and so on, that is important. So here also we'll see that one can deduce in a similar way. I will not say that exactly same, in a similar way, which is called the Kolmogorov-Chapman equation. So here actually what I try to write down, that P of t plus capital T. So this is a matrix, no? P of t, because I wrote down this P of t. No, this is the matrix. So P of t plus capital T, you will see that this is will be PT and then P of t. This is a matrix multiplication. So that is called the, this is called, okay, I'll do it. I'll first write down. This is Chapman-Kolmogorov equation. Okay, how to do it? This is in the matrix notation, and then I'll try to write down in a element wise. Okay, so now element wise you will see that how to find out these things. Okay, let's see. So now I start with any element from the left hand side, which is Pij of t plus capital T. Is it not? So this is nothing but probability of x of t plus capital T is equal to j given x of 0 is equal to I. Is it not? So now by using total probability law, I can write down this is summation over k probability of x of t plus capital T is equal to j, maybe the intermediate time x of t is equal to maybe k given x of 0 is equal to I. Is it not? So this is by using the total probability law. Okay. So now these things actually if you write down, this is a conditional probability. So I can think of this is summation over k probability of x of t plus t is equal to j, x of t is equal to k, x of 0 is equal to y divided by probability of x of 0 is equal to I. Okay. So now if you try to write down this part, I can multiply it and divide something. So this actually I can write down that probability of just looking at the things. If I just try to have this form, so probability of xt is equal to k and x of 0 is equal to I. If I multiply by these things, probability of x of 0 is equal to I, then I need to divide that part. So now probability of x of t plus t is equal to j, then x of t is equal to k, x of 0 is equal to I, and divided by probability of x of t is equal to k, x of 0 is equal to I. So over k. So now this part, okay, this is nothing but what? This is nothing but probability of x of t is equal to k given x of 0 is equal to I. Is it not? And this part is nothing but probability of x of t plus t is equal to j given x of t is equal to k, x of 0 is equal to I. Is it not? So now these things actually I can write down probability of k. So now this is nothing but what? This is nothing but my p I k at t. Is it not? By definitions. Now this one, so now xt is a Markov chain. So now we have 3 points. Okay, so it satisfies your Markov property. In particular, what I can write down, this is same as my probability of x of t plus capital T is equal to j given, because xt, that is the current point, because 0, t and t plus t. So this is x of t, which is actually k. So now this is same as over k, pik of t. Now this one, what I know, that my chain is homogeneous, or not the continuous time Markov chain, it is homogeneous. So this is nothing but same should be that probability of xt, okay, I can have that k and j to capital T. Is it not? Because of the homogeneity. Homogeneous CTMC, so I have this part. So what I have here, if you look at, I have Pij of t plus capital T. Now I have in this part. So now if you look at in a matrix form, this is nothing but, so in matrix form, what I have, P of t plus capital T, this is my P of t and then P of capital T. Is it not? Okay. So we'll see that we'll use this one to have something later. Okay. So let us make the following remark. If I denote PJT, which is the distributions of probability of xt is equal to j. Okay. PJT is equal to probability of xt is equal to j. Then my claim, then summation over j over your s pj of t, which is actually 1 for a CTMC. Why this is so? Because what I have, so what is your PJT? PJT, this is my probability of xt is equal to j. So now again I can use the total probability law. This should be summation over say maybe I is in my state space S. Probability of xt is equal to j and maybe x0 is equal to I. So now if you try to write down these things, this is same as my summation over I is in H. So this part I can think of, this is probability of x of 0 is equal to I, and then probability of xt is equal to j given x of 0 is equal to I. So this is nothing but I have summation over I is in my S. This part is Pij of t, and then I have probability of x is equal to 0, which is the initial distributions. Okay, I denote maybe small pi I. So small pi I is equal to probability of x of 0 is equal to I. This is the initial distributions. Okay. Okay. So what I know, so this implies summation over j is in my S, Pj of t, this is summation over I is in S, summation over j is in my S, Pij of t, and then pi I. So now probability of x0 is equal to I, and so that means summation over I of pi I, it should be 1, no, because the x0 taking values in the state space, and so the probability of that thing should be 1, and hence you see that this is 1 because summation over j Pij of t, this is actually 1 I have, so you can interchange because all these are positive and so on. So you have this is 1. So summation over j is in S, Pj of t is equal to 1. Okay. Okay. So what we have seen for your discrete time Markov chain, that if one step transition probability matrix is given to you, and if you know the initial distribution, then you can describe your DTMC completely, is it not? So here, in a similar kind of concept, but here you have the time continuity and so on. That is why I need to think of something called the rate matrix. Okay, so idea is actually, if I know the rate matrix, then I can completely determine my CTMC. Okay, so because of the time is involved, I need to have some rate. Okay, so if I know the rate actually, then I can find out. So for that I need, that is called the transition density matrix. I'm defining for that. So now suppose you assume that this quantity Qij, what is this? This is nothing but the ddt of Pij of t at t is equal to 0. So it exists. Okay, so assume that. So that is what is your Qij? So later on actually we will declare this Qij is basically the rate matrix or the density matrix. So you see that the rate, no, at t is equal to 0. If we know that t is equal to 0 because of the time homogeneity and so on, so it is enough. Is it no? That is the rate. Rate means for one case actually, if you know, that is fine. So then Qij, this is nothing but limit h goes to 0, Pij of h minus Pij of 0 by h. So you can check it easily. That means I can think of Pij of h, for h is infinitesimal time. This is, I can write down that 1 plus h of Qii plus small o of h for I is equal to j, and this is h of Qij plus small o of h for I not equal to j. Okay. So I'll come back to this little later whenever I am considering again the Poisson process. I told you, there are two ways to define the Poisson process. One is given to you the rate and so on from there actually. So from here it will be clear why that is so. So what is your small of h? You know that it is a function of h such that if it is say f of h, then f of h by h at h goes to 0. So f of h by h goes to 0. That is the small o is function. Okay, so now I denote that q. Okay, so this q I am denoted as Qij. This q is called the rate matrix or the transition density matrix. In which rate the transition is happening. Okay, because suppose you are at state at time point t, you are in state I, so then you actually want to jump to state j in which rate? Okay, so qij, it gives you the rate of jumping and so on. Okay. Okay. So now we can check that qii is non-negative. It may be 0 or negative. qij, they are positive for I not equal to j, and summation over j qij, they actually 0. Okay. Okay. So this matrix Q is known as the rate matrix. So as I told you, that Poisson process you have two ways to define it. In particular, so suppose I have, okay, let's consider one example. So NT, this is a Poisson process. With intensity, say lambda. Okay. I'm saying that it is a continuous time Markov chain. And if you consider, say, infinitesimal time, what is my pi plus 1 over h? This is nothing but probability of n of h is equal to, if h is very small, infinitesimal time, is equal to 1. Is it not? So now this is, I have already defined there that this is lambda times h plus small o of h. Okay. And this is I to I plus 1, no? So that is the jump size is length 1, no? There. So that is n of h is equal to 1. Probability of n is equal to, this is lambda of h plus small o of h. So this lambda I have from here. And what is your Pij of h? Whenever I put it, that if the infinitesimal things is greater than 2, that means if, say, j is not equal to I and I plus 1, so then this should be small o of h. For j is not equal to I plus 1. And what is your Pii of h? This is nothing but probability of n of h plus, sorry, this is t plus h is equal to I given n of t is equal to I. Is it not? So that means this is same as, I can write down this part, no? Probability of this part. So this is same as now, nothing but n of h is equal to 0, and now this is 1 minus lambda h plus small o of h. In this way, actually, we have defined it there. Two way to defining your Poisson process. So from here, actually, what you will see, Pii equal to 1 minus lambda h plus o of h, Pij of h for I not equal j not equal to I to I plus 1 is order of h, and then Pii plus 1 is equal to lambda h plus order of h. So now if you just, from here, actually, if you just think of, okay, for infinitesimal small h, then I can find out the transition rate matrix or the density matrix of your Poisson process. So Q, in this case, what I have, this is minus lambda 0 0 0 0 minus lambda 0 0 and so on, 0 minus lambda 0 0 and so on. Okay. Okay, so this is the rate matrix or the transition matrix for Poisson process. Okay. So as I told you that if I know the red matrix Q, then I can find out the transition probabilities. Okay, or I can completely determine your CTMC. So towards that, I am going to prove so-called the Kolmogorov's forward equation or Kolmogorov backward equation. So here I will use my Chapman-Kolmogorov equation. So in particular, what I try to say, okay, so this is Kolmogorov forward and backward equation. Okay, so what it says that, so now for any h is positive and say t greater equal to 0, I try to find out my Pij of t plus h minus Pij of t by h. Okay, so what is this? These things actually I can write down. So Pij of t plus h, this actually I can write down. So this is 1 by h of, this part I can write down. This is summation over k Pik of h Pkj of t, because I just write down this Pij of t plus h, only this summation form, and minus I have Pij of t. So now this part I can write down. This is 1 by h. If I put say k is equal to I, k is equal to I, so this is Piih, and then I have Ijt, so I can take common. So what I have, Pii of h minus 1 times Pij of t. Okay, and for k not equal to I, what I end up with, plus 1 by 8 summation over k is not equal to I have Pik of h and then Pkj of t. Is it not? This part I have. So here I am using this part which is coming from your Chapman-Kolmogorov equation. So this is because of Chapman-Kolmogorov's equation. Is it not? So this implies if I send my limit as h goes to 0, so the left hand side is nothing but my Pij prime of t. Okay, and this one now Pii h minus 1 by h, and so what is this? If you look at here, that for I is equal to j, so Pii minus 1 by h, that is equal to Qii plus small a of h by h. So at h goes to 0, so this thing goes to basically Qii. Is it not? Because small o of h by h, that goes to 0 as h goes to 0. So from here what I have, Pij prime t, this is, so from here I have Qii and then P of Ij of t and then plus. So now here you see that Pik h by h, as limit h goes to 0, then this should be nothing but Qik. Is it not? Because I not equal to k. Just look at the definitions. Because small of h by h, again that goes to 0. So what I have, this is summation of k is not equal to I Qik times Pkj of t, because this is independent of h. So now these things I have. So that means in a matrix notation, what I can write down, in matrix form, what I have, that P prime of T, whose element are Pij prime of T, this actually I can write down, this is Q times P of T. Okay, and already you have seen that P of 0, which is basically identity matrix. Is it not? This is the identity matrix. Okay. Because that is delta ij, no? Pij of 0 is equal to delta ij. Okay. So this is called Kolmogorov's backward equation. This is known as Kolmogorov's backward equation. So you are familiar with how to solve this equation. So it is, you can think of it is a system of, okay, here the system may take, I mean, it is countable, no? It may take infinite things, but at least for how to solve this problem, no? So this is that e to the power q form t of a times identity and so on. So the solution to this problem, okay, let me do this thing. This is for the Kolmogorov's backward equation. I will come back to that. So now Kolmogorov's forward equation, what it says that P prime T is equal to, I can also write down P prime T as a Pt of Q. Okay, this is called Kolmogorov's backward equation. No, forward. Sorry, forward equation. Because Pt is in the left. So Kolmogorov forward equation and that. So depending on which part you are trying to calculate, which Pij and so on, depending on that, either Kolmogorov forward equation is more useful or Kolmogorov backward is more useful. Okay, so how to deduce that part? This is nothing but actually, if you just think of, okay, I put Pij of T plus H. This is, I wrote down little different way. K is in my S. I put it again Pik, but here I put as a first T. So initially, for my first case, I consider H, Pik H, and then Pkj of T. But I can consider also this is same as K is in S Pik of T, and then Pkj of H. Is it not? So now if you try to find out this Pij of T plus H, okay, by using this, which is coming from your Chapman-Kolmogorov equation. Now if you calculate this Pij of T by H, limit H goes to 0. These things, which is exactly same as my Pij prime of T. Now you see, you will end up with exactly Qjj of Pij of T plus summation over k is not equal to j. I have Qkj and then Pik of T. Okay. And now you will see that these things should be exactly, okay, I wrote down these things. So in a matrix notation, you will see that it will be of this form, P prime T, which is equal to Pt times Q. Okay, because Qii is a negative and summation over Qij over j, that gives you 0. Okay. Okay. Let us come back to this ODE. P prime T is equal to Q times P of T, where Q is your infinite matrix in general. Okay, it may be finite matrix because depending on your state space. If state space is finite, Q is finite, and so on. So now the solution to this problem, maybe I put as a star. So solution of star can be think of or can be written as okay, solutions of star have the following form. So which is PT, which is identity plus summation over n is equal to 1 to infinity t to the power n q to the power n by n factorial. Okay, this part maybe you know. And so now if see it is an infinite sum and we don't know whether it will converge or not in general, but at least for finite dimensional matrix, means if q is finite dimension, so if q is finite dimensional matrix, I know that this above series is convergent and it has a unique solution. Okay, unique solution exists. Now how to find out that part, that is not easy actually. Okay, so in general for q infinite dimensional we cannot say anything else whether it is convergent or not and so on. So one is to then put some conditions so that it will converge and so on. In particular, if you look at, if you consider the norm of q is less than 1 and so on, so it will converge and all these things. That is all the matrix calculation. But in particular, if you have q which is finite dimensional and say suppose it is diagonalizable. See, because you have this matrix, no? I plus this thing, so it is nothing but no, e to the power t of a. So this is actually e to the power tq. Is it not? Because if you think of my t and t of q is equal to just x, this is again the matrix things one is to think of. So then this is exponential. This series is basically nothing but the exponential series. So at least for some special case, in particular, if q is finite dimensional matrix and diagonalizable, and suppose it has a say distinct eigenvalues, okay, which I consider beta 0, beta 1 up to beta n. Suppose it has a n dimensional finite dimensional matrix, I am thinking as a dimension n. So it has say beta 0, beta 1, beta 2 up to distinct eigenvalues. Okay, it may not have, so in that case one is to look for the Jordan block and so on, and then you try to compute your this this matrix e to the power tq. Okay, there you have finite things, no? For the finite case you have something like that. So now if you have q which is finite dimensional and diagonalizable, all are distinct eigenvalues, say beta 0, beta and beta, then what I can write down, then there exists a matrix A which is invertible such that it is similar to my q. That means I can think of my q which is A D A inverse. And what is your D? D is nothing but the diagonal matrix with entries which is beta 0, beta 1 up to beta n. Okay, so D is a diagonal. That part you know already from your linear algebra class or something like that. Okay, because I want to find out the solution to that problem. P prime T is equal to say QPT or PT of, okay, whatever, maybe Q of PT, and you have P0 is equal to identity. So then what the matrix P takes, in that case PT, it should be A D1T A inverse. Okay, then what is your D1 now? D1 of T, This is again the diagonal matrix, but now the diagonal entries as e to the power beta 0, e to the power beta 1, e to the power beta n. Okay, e to the power beta n. So sorry, beta n because it is time t should be there. Okay, so now pt I am having from a d1t a inverse, so I can calculate my pt. So here what I want to know that if I know my q, even from your Kolmogorov's equation, forward or backward, what it says that if you know q, then I can find out my transition probabilities matrix P. Okay. So the rate matrix is more important, is really important for CTMC. Okay, so I'll come back one example where you can directly use Kolmogorov's equations and try to solve it, or maybe I'm just trying to use this matrix formations for the finite case. Okay, let us make one remark. I can have exactly similar way that if I know only the state probabilities Pt, which is the state probability vector, what do you mean by that? So Pt, this should be my Pj of t. Okay, this is a vector P1t, P2t, and so on, or not maybe P1 depending on your j is in from your s. Where Pj of t, I am thinking that probability of I already defined no initially xt is equal to j. So already you know that summation over j pjt is equal to 1 for all j and so on, is it not? So you can check yourself that I can find out again the Kolmogorov's backward and Kolmogorov's forward for this state probability vector also, in particular p prime t, which is my pt and q, or I can think of p prime t, which is q of pt. Accordingly, you need to think of means here it should make sense, no? Because it should be a vector, so maybe a transpose or whatever you are considering. So it is in this form. Okay. So that means we can solve to get pt if the initial probability distribution P0 is given to you and the rate matrix Q. Okay, so you can find out your small pjt if the initial distributions and then the rate matrix is given to you, you can solve this problem. Okay, let us consider one example where my Q is given to you. How can I find out my transition matrix Pijt, or the element of this thing? That example is called the two-state chain. So chain has two states, say 0 and 1, something like that. Okay. So consider a CTMC two state, maybe 0 and 1. So basically I can think of 0 and 1, they are the state such that chain spends say an exponential time with rate lambda in state 0 before going to state 1. Okay, so basically you have two steps, 0 and 1. Okay, so it stay here. What it says that exponential time with rate lambda, it spends at at 0 before it jumps to my state 1, and then it spends some another exponential time with rate mu, and then actually before it jumps to state 0. So before going to state 1, where it spends an exponential time with rate mu. So rate is more important. This is mu before returning to state 0. Okay. So that is what is your Q matrix in this case. This is minus lambda, lambda, mu and minus mu. Okay. Q is minus lambda, lambda, mu and minus mu. So I want to find the probability transition matrix. Okay. So rate matrix for the two-state chain is minus lambda, lambda, mu and minus mu. Okay. Having this part. And I want to find out the transition probability matrix. So for that, what I need to know, that I need to use my Kolmogorov's backward equation or maybe Kolmogorov's forward equation. So now since Q is finite, and what I know that if Q is diagonalizable, then I can write down easily, using this matrix calculations. So that is, I will show you the two solutions. One is using the matrix method. This one is called the matrix method, and another is directly using the Kolmogorov's backward or forward equation. Okay. So let us first consider the matrix method. This is possible here because Q is finite, and already we just give one special case that if it is diagonalizable and all the eigenvalues are distinct, then we have in a good form. Okay, so let us do that things. So Q, I'm saying that Q, it has eigenvalues which is 0 and then minus lambda plus mu, which is distinct. Okay, you check yourself. You know how to find out the eigenvalues and so on. So look at this determinant of A minus Q minus lambda I is equal to 0. From there you will find out. And the corresponding eigenvectors you check it, this is 1 1 and then lambda minus mu. Okay, so we already know that what will be your A is basically linearly independent vectors, eigenvectors, which is coming from that eigenvectors of your Q. That is the A, because it is self similar to A. Q is self similar to A. So in that case, my A should be 1 1 lambda minus mu. Okay, and A inverse exists, so A inverse should be you check it, this is 1 by lambda plus mu, because it is only 2 cross 2 matrix, so one can easily find out your A inverse. This is mu lambda 1 minus 1, is it not? So consider the A transpose and so on, so you know all these things. Okay, so then what is your D now? D should be the diagonal matrix with diagonal entries, which is basically the eigen values. So it should be 0 0 and then minus lambda plus mu and then 0. Okay, so hence now it has a distinct thing. So what I know that PT, which should be A D1T and then A inverse, is it not? So what is my D1T? This is again the diagonal matrix with diagonal entries, which is e to the power now 0 t and then e to the power minus lambda plus mu of t. Is it not? So now if you find out your pt, this should be 1 lambda 1 minus mu 1 0. This is nothing but your 1. This is 1. So 1 0 0 e to the power minus lambda plus mu times t, and then I have 1 by lambda plus mu times mu lambda 1 minus 1. Okay. So now if you do this matrix calculation, what I have, this is 1 by lambda plus mu plus lambda e to the power minus lambda plus mu times t, lambda minus lambda e to the power minus lambda plus mu times t, mu minus mu times e to the power minus lambda plus mu times t, and then lambda plus mu e to the power minus lambda plus mu times t. Okay, you just check yourself. Maybe in my calculation I may made mistake, but you check yourself. Okay. Okay, so the pt I have in this form. So now pt, now I have the 4 element p11, p12, pt1 and p22. So you have your p11t is nothing but this one, p21t this is nothing but this one. Okay. Okay, so let's see if you try to use the direct approach. So now if you use the Kolmogorov's forward equation, Kolmogorov's forward equation, what it gives, that p00 prime t, this gives you mu times p01t minus lambda times p00t, and these things actually I can write down. This is minus over lambda plus mu times p00t plus mu. Why this is so? Because that p01t is equal to 1 minus p00 of t, because summation over j pij of t is equal to 1. So now we have j is equal to 0 and 1. So I have this part. Okay, p01t is equal to 1 minus p00 of t. So this part I have p00 prime t is equal to minus lambda plus mu p00 t plus mu. So this is a simple ODE. What you can solve it, that e to the power lambda plus mu t p00 of t, this is equal to mu by lambda plus mu, means you just multiply it by the integrating factor, which is e to the power lambda plus mu of t, and then if you do these things, so we end up with lambda plus mu times t plus c. Okay, so this implies p00 of t, this is mu by lambda plus mu and plus c times. So now what is my c? I need to find out. C actually, see, p of 0 0 of 0, this is 1, no? That is, we know that p ij of 0 is equal to delta ij. So p of 0 0 1 is equal to 0. This part I know. So this implies my c should be lambda by lambda plus mu. Is it not? Just if you put it here, p00 is equal to 1. So this part gives you mu by this part. So this is 1. So c is equal to of this part. Okay. Okay. So what I have then, P00t, then mu by lambda plus mu plus okay, c times I have e to the power minus lambda plus mu times t, no, because I have to multiply it by this part minus of that. So I have lambda by lambda plus mu e to the power minus lambda plus mu times t. So now if you see from here in my matrix, I have exactly that part, no, mu by lambda plus mu plus lambda by lambda plus mu times e to the minus lambda plus mu by t. Okay, so once I got P01t, then I can find out, no, P01 also. That is easy one because I know that P01t plus P00t is equal to 1. So you can find out your P01t. Similarly, you can check P11t, which is lambda by lambda plus mu by lambda plus mu to the power minus lambda plus mu times t. So here you see later on actually we'll consider the limiting distribution. So in this case, at least for these two state chain, as t goes to infinity, so now P11t, this is lambda by lambda plus mu. Okay, as t goes to infinity. And P00t, as t goes to infinity, that converges to mu by lambda plus mu. Okay, so in this case, that limiting things exist at least. As t goes to infinity, P11t is equal to this part, P00t is equal to this part. Okay. Okay, I'll come back to these things in a later state. But what it says that if you know the transition rate matrix Q, then I can find out my probability transition of transition probability matrix P. Okay, so another example I will consider. I want to calculate P0j T for a Poisson process with a rate lambda. Okay, so I'm not going to do the things, but idea is one needs to define something which is basically your generating function with respect to my small pjt. So if you define pjt, which is say p of 0j of t, okay, then you define say pi of small s of t, which is summation over j is equal to 0 to 0 s to the power j pj of t. Now use the Kolmogorov's say forward equation, which is nothing but p00 prime t minus lambda p00 of t p0j prime of t, which is equal to minus lambda p0j of t plus lambda p0j minus 1 of t for all j greater equal to 1. Okay, this is from Kolmogorov's forward equation. Okay, so now you end up with that my pi of st, because you just consider the differentiations of your with respect to t of pi of st. Okay, then you have pj prime t, because that is actually we know it, no, pj prime of t, which is coming from there. Okay, this is my short notations I am using, and then you can write down p00 and then p0j prime t using this formulation. But you have that dot t of pi of st, this is actually lambda times s minus 1 pi of s and t. Okay, so what is your pi of s0? this is actually summation over j is equal to 0 to infinity s to the power j and then pj of 0. Is it not? So pj of 0 means this is summation over j is equal to 0 to infinity s to the power j. Pj of 0 means pj, which is p of 0j of 0. Is it not? So now what I know that p ij of 0 is equal to delta ij. So that means whenever j is equal to, in this case, if j is equal to 0, then it gives you 1, otherwise it is 0. So j is equal to 0, so you have s to the power 0, that gives you exactly 1. Okay, so now you have PDE form. So dot T of pi of st is equal to, basically actually it is a ODE, because s is fixed, you can think of. So something f prime t is equal to lambda of s minus 1 of ft, and then f of 0 is equal to 1. So from there what you have, pi of st is exponential of lambda of s minus 1 times t. Okay, which is nothing but the probability generating function of the Poisson process is it not? Or the Poisson distribution with lambda t distribution, no? With a Poisson random variable with intensity lambda t. So thus, with, okay, maybe this is a probability generating function of the Poisson distribution with intensity say lambda t. So how do you know that probability generating function uniquely determine the distributions? Is it not? So thus, what I have, that P0j of t, this is nothing but my P0t. This gives you to the power minus lambda t times lambda t to the power j by j factorial. Okay. So P0j is given by this formulations for my Poisson process. Okay, so this one probability of x is equal to j already we know directly, no? But here actually we try to use our continuous time Markov chain concept, and using the Kolmogorov forward equations, we are having this part. Okay. Okay. I'll consider something. Basically, as you see that here I have states say I, j, and so on. So now that before jumping to state j, no, Markov chain, how much time it waits there? What that is basically the waiting time. So I want to know what is the distributions of waiting time. If the chain start at state I, and if you denote say tau I, which is the spend time at state I, or the waiting time, before jumping to another state, okay, or before moving to. I want to know what is the probability of tau I. Oh, sorry, what is the distributions of tau I? Okay. So probability of tau I is greater than. So actually, what we know the memoryless property basically for the exponential distributions, is it not? So if I have something like that, so probability of say x is greater than t plus s given x of that probability of sorry, what did I write down? Probability of x is greater than t plus s given x is greater than t. If it is same as my probability of x is greater than s, then we know that it is nothing but basically called the memoryless distribution, memoryless property. And we know that that means basically x follows a exponential distribution, is it not? We'll try to show here that this tau y, the span time, it is follows a exponential distribution with mean which should be minus 1 by qii. Okay, because qii is negative, that is why minus 1 by qii, it should be positive. How to check that part? So for that, I need to know the time homogeneity or the homogeneous continuous time Markov chain, homogeneous property. And we know that probability of say A intersection B given something the same as probability of A given something given B. Okay. So in particular, if I consider probability of tau y greater than t, so then what is the meaning for that? That starting with state, this is nothing but the probability of x of s is equal to I. Okay, for all time 0 less equal to s less than equal to t, starting with my x0 is equal to I. Is it not? Tau y, which is the span time, starting with state I. So now tau of I is greater than t. That means basically that up to time t, it is no x of s is equal to I, given that x of 0 is equal to I. So now this part, okay, there I am not using here in this case actually, but one can do it, and there are two ways to do these things. So I can write down these things as a probability of x of s is equal to I for all 0 less than equal to s less equal to say t by n, given x of 0 is equal to I, then probability of x of s is equal to I in the time interval t by n less than equal to s less equal to 2t by n, given my x of t of n is equal to I, and so on. Probability of x of s is equal to, now I should have n minus 1 times, okay, xi is equal to I, but it is from n minus 1 t by n less than equal to s less than equal to t, given x of n minus 1 times t by n is equal to I. Okay, they are independent because it is a Markov property holds. Okay, using that part, I'm writing these things, and because of the time homogeneity, if you look at the length, is nothing but actually t by n, and hence this part I can write down. This is same as my probability of x of s is equal to I, such that 0 less equal to s less equal to t by n, given x of 0 is equal to I. This is whole to the power n form, because all these part is same as my probability these things because of the time homogeneity. Okay. So what we have, probability of tau I is greater than t, I can think of then this is nothing but that limit n goes to infinity. Okay, because the right hand side is independent of my n, so I can take the limit as n goes to infinity. Probability of x of s is equal to I s less than equal to t by n given x of 0 is equal to I all to the power n. Okay, so now this one I can think of, this is limit n goes to infinity, probability of x s is equal to I in the time interval. So t by n is now really infinitesimal small time interval. X of 0 is equal to I, given x of 0 is equal to I. So then this you can think of PII form. No, because of the smallness. So and PII, what I know, that is 1 plus QI of infinitesimal that point at time h. So now in this case, this is t by n. Okay, and then plus small o of t by n to the whole to the power n. So now this is nothing but, so it is something like that 1 plus x by n to the power n as n goes to infinity. That is another formula of e to the power x. So this is nothing but e to the power t of qii. Is it not? 1 plus x by n. This is tii qiit because small o t by n, forgot about because that goes to 0. So this is of this form, limit n goes to infinity, 1 plus qii of t by n to the power n. So I have something like that to the power x. I can write down limit n goes to infinity, 1 plus some x by n whole to the power n. No, there is another form that e to the power x. This series converges to the power x. Sorry, sequence. Why it is series? Sequence. Okay. So e to the power ti greater than t. So this implies probability of tau I less than equal to t, which is the distributions of tau I. This is 1 minus e to the power 1 minus e to the power t q I I. Okay. So this implies tau I. This is exponentially distributed with mean now minus 1 by qii. Okay. Okay. So I have, maybe I can consider one more example and then I'll stop it a little bit. Other than that, as I told you, you can just start with probability of tau I greater than t plus s given tau I greater than say t, then you end up with this is same as probability of tau I greater than s. Okay, for any t and s positive. So from there you can say that tau I is exponentially distributed. But here actually I am giving the mean also. Okay, giving the mean also. Okay, so consider a CTMC with rate matrix Q, which I have minus 5, 3, 2, 1, 1 minus 3, 2, 2, 4 minus 6. No, I can think of rate matrix so that the idea should be QII should be negative and then Qij should be positive for I not equal to j and summation over Qij over j should be 0. Is it not? So now 5 minus 5, 3, 2, 1 minus 3 and so you can make yourself many Qij. And the initial distribution So lambda, which is 0, 0, 1. Okay, so now we have 3 states. That means it starts with state 3. So I want to find out probability of tau is greater than t, where tau denotes the first transition of the chain. So as I said that in this case is nothing but say 1, 2 and 3. Okay, so from the initial distribution what it says that the chain start at state 3. Is it not? So then probability of tau is greater than t, what it says that this should be to the power t of q33. That is why that I means start state I and then how much time it will spend there before jumping to another state. So it start. So this initial distribution gives you that from where actually it is started. Okay. So tq33, which is nothing but e to the power minus 60. Okay, so I'll stop now and next day I will complete the other parts and then the limiting distribution of CTMC.